In this lesson and the next few, we will discuss how to use a specific mathematical formula called Bayes' rule or Bayes' theorem to help us make decisions when the information available is uncertain or ambiguous. Since this is such a powerful tool and becoming more common, especially in the area of data analytics, big data, artificial intelligence, and intelligence analysis, it is important that you understand the concept, the math behind it, and are able to apply it in the area of predictive intelligence. As a predictive intelligence analyst, you can't be lazy and abdicate your thinking to someone else's software application. While it's helpful to leverage technology, you must understand the math, logic, and algorithms behind the technology, so you'll know its strengths, weaknesses, and where you must intervene. To this end, I'll end this section by showing you how to use Microsoft Excel to help you apply Bayes' rule and make intelligence predictions. Also, I provided several other resources within each lecture if you'd like to learn more about the technical and mathematical applications of Bayes' theorem. Bayes' theorem is a probability theory originally developed by Thomas Bayes, an English statistician, philosopher, and Presbyterian minister. Bayes never published the theorem, but his notes were edited and published by Richard Price after Bayes' death. Richard Price, a friend of Bayes, was also a Protestant preacher, mathematician, and Welsh philosopher. However, Bayes' theorem was greatly expounded upon by the French mathematician Pierre-Simon Laplace. Most of what we consider the Bayesian interpretation of probability was developed by Laplace. Bayes' theorem wasn't without controversy. It was attacked by many who considered themselves math purists and thought Bayes was quasi-science. In particular, there was a debate of Bayes' role in statistics between those who thought statistics should be based solely on the collection of lots of data, the frequentists, and those who thought that Bayes could be used to make estimates where the data was difficult to collect or non-existent. Because of both the utility for which Bayes lent itself to solve complex problems of probability and for the controversy that came with it, Bayes was often used in secret to solve problems for which the frequentists had no answers. In short, Bayes' theorem can be seen as a way of understanding how the probability that a hypothesis is true is affected by a new piece of evidence. It has been used in a wide variety of contexts, ranging from astronomy, marine biology, to highly classified intelligence work. Bayesian thinking is the basis for the development of artificial intelligence today. With that short introduction, let's build on your familiarity with probability from the previous lessons in this course and use a simple example to help us examine the Bayes' theorem conceptually. I have two cups, cup A and cup B. They aren't labeled, so you don't know whether cup A or cup B is red or blue. If you pick one of the cups at random, which is the probability that you'll pick cup A? Since there are two possible outcomes and only one desired outcome, the probability that you'll pick cup A is 1/2 or 50%. Normally, possibilities are represented on a scale of 0 to 1, with 0 representing an impossibility or 0% and 1 representing certainty or 100%. Now, let's use some basic geometry to examine the concept. This area represents all possibilities. So in the instance of our previous example, it represents both cups A and B. And since it represents all possibilities, its probability is 1. If I want to divide this area to represent the two distinct yet equal possibilities from our previous example, then I would cut this area in half. The two cups are represented by the two halves, so it's easy to see that each half represents one of the two cups, A or B. Thus, the chance that your cup is cup A is 1/2. Likewise, the chance that your cup is cup B is 1/2. Now let's say that cup A has 10 red marbles and nothing else. Then we'd show that by coloring red the entire space that represents cup A. Likewise, cup B holds 10 blue marbles and nothing else. So we depict that by coloring the entire space that represents cup B as blue. You still have your cup and you can't see inside of it, so you still don't know whether you have cup A or cup B. But now you reach into your cup and you pull out a red marble. Which cup do you have? That's right, you have cup A. Let's try another example. In this instance, cup A contains 10 red marbles and cup B contains 5 red marbles and 5 blue marbles. We depict the proportion of red and blue marbles each cup holds by coloring in the corresponding areas appropriately. Again, you choose a cup at random, not knowing which is cup A and which is cup B. You reach into your new cup and you pull out a red marble. Which cup are you most likely holding? It's possible that your cup could be either A or B, since both cups contain red marbles. However, since your cup A has more red marbles, it's more likely that you're holding cup A. But why? Since you drew a red marble from your cup, we can eliminate the areas that don't contain red marbles for this particular outcome. This means that the probability that you're holding cup A is now twice as likely as holding cup B. This doesn't eliminate the possibility that you're holding cup B, it just means that the evidence suggests that possibility is now less likely than before. Specifically, since there are 3 equal areas, 2 in cup A and 1 in cup B, the probability that you're holding cup A has changed from 1/2 to 2/3. The probability that you're holding cup B is now 1/3. Let's move from a geometric expression of Bayes to an algebraic one. As a reference for the mathematically inclined in the audience, I'm using the simple form of Bayes' rule, which means I'm using a denominator that is expressed a bit differently from the general rule. The formula can be a bit confusing, so let's look at it one piece at a time. First, what we want to discover is the probability of our hypothesis being true, supposing that our new piece of evidence is true. This is represented as P for probability, H representing the hypothesis, the vertical bar represents a conditional property, and E represents our new evidence. We have 2 hypotheses in this example, so let's determine the probability that you chose cup A, given that you drew a red marble. We compute this using 3 key factors. The first is our prior probability of the hypothesis being true, shown here as P sub h. We call it the prior, or the base rate, because this is the probability we assign before we have any evidence. In this case, we assign it 0.5, because there are only 2 possibilities, and lacking any additional evidence, we assume that both possibilities are equally true. The second is the probability of the evidence given an hypothesis, written as P sub E given H, which means in this example, what is the probability that we'd select a red marble from cup A? Since cup A only contains red marbles, the answer is 1. Last is the prior probability of the evidence. Since there were a total of 15 red marbles out of a total of 20 marbles, the probability that you'd select a red marble, given either hypothesis, is 0.75. Thus, the probability that we drew a red marble from cup A is 2/3, or roughly 67%. And the probability that we drew the red marble from cup B is 1/3, or roughly 33%. These probabilities are based on the simple fact that cup A contains more red marbles than does cup B. In summary, Bayes' rule can help you calculate conditional probabilities. To do so, you must know or estimate 3 things: the prior probability, the conditional probability of the evidence for a specific hypothesis, and the probability of the evidence independent of any hypothesis. I hope this explanation of Bayes' theorem was helpful. In the event that you found this lesson either was too simple or too complex, I've included some additional resources to help you better understand the concept. Please be sure to review them before continuing to the next lecture.